Welcome to this explainer. Today, we are taking on literally the ultimate cosmic whodunit. It's a mystery that has completely baffled the brightest minds in astrophysics for nearly a century now. We're going to examine the evidence, track the invisible clues, and line up the suspects in what is arguably the greatest open case in the entire universe. Yep, we're talking about the hunt for dark matter.
To kick things off, I want you to try something. Just look at your own hands for a second. You, the device you're watching this on, the Earth, the stars, literally everything you have ever seen, touched, or interacted with, it's all made of normal baryonic matter. But here's the crazy hook. All of that normal matter makes up just 15% of the total matter in the universe. Think about that. That means you are the actual anomaly in a universe that is completely dominated by a staggering 85% of missing mass.
Okay, let's dive into this, because you have to ask, if the vast majority of the universe's matter is completely invisible, like it doesn't emit or reflect any light whatsoever, how do we even know it's there? Well, to understand how we can confidently say 85% of the universe is just missing, we have to look back at the trail of clues left by gravity itself.
Section 1. The Missing Mass Mystery.
Our investigation actually begins in the realm of the very large. We're turning the clock back to the early days of modern astronomy, where the first weird signs of this abstract puzzle started emerging from the darkness. Back in the 1930s, an astronomer named Fritz Zwicky was observing the Coma cluster of galaxies, and he realized they were moving incredibly fast, like dangerously fast. So fast they literally should have flown apart based on the visible mass alone. There just had to be some unseen matter binding them together. Then, fast forward to the 1970s, and Vera Rubin found that the outer edges of individual galaxies were spinning at these absolutely surprising velocities. It was basically undeniable proof that galaxies are encased in massive halos of invisible mass.
Section 2. Gravity's invisible scaffolding.
So we know this invisible mass holds galaxies together today, right? But its role goes way deeper than that. It actually fundamentally shaped the early universe right from the very beginning, and this brilliantly illustrates exactly what we're talking about. What you're seeing here is a simulation of the cosmic web. Because dark matter didn't interact with the hot, intense radiation of the early universe, it started collapsing under its own gravity super early on, forming this immense, complex network of dense filaments. It was essentially the scaffolding for reality. Once normal matter cooled down, it simply fell into this dark matter framework, and that's what ultimately built the galaxies, the stars, and the planets we live on today. Now, since we obviously can't see this scaffolding directly, astrophysicists have to rely on a primary tool to spot the invisible clues left behind, and that tool is gravitational lensing. According to general relativity, the sheer mass of dark matter actually curves space-time itself. It's wild to think about. When light from distant background galaxies passes through this warped space, the light rays get deflected and distorted. This can happen as weak lensing, which creates subtle little distortions across huge patches of the sky, or strong lensing, which drastically bends the light. To put that into perspective, here's how this invisible mass warps light through strong lensing in practice. A massive cluster of dark matter in the foreground acts exactly like a giant magnifying glass. As light from incredibly distant, ancient galaxies travels towards Earth, it passes through that cluster's dark matter halo. The strong lensing effect drastically bends the light, magnifying and distorting those distant sources into visible arcs and rings. By measuring these exact distortions, we can perfectly map the location and density of the invisible dark matter that bent the light. It's like catching the invisible man by looking at the deep footprints he leaves in the snow.
Section 3. The bullet cluster smoking gun.
Okay, so we've seen the gravitational effects, but for a long time, skeptics argued, hey, maybe our understanding of gravity is just wrong. To put that argument to rest once and for all, astronomers needed a smoking gun. And man, did they find it in the aftermath of an incredibly violent cosmic collision. Now, what's really interesting here is the stunning separation of colors. This is the famous bullet cluster, which was formed by the violent crash of two massive galaxy clusters. The pink areas represent the normal baryonic matter. That's hot gas that crashed together and got slowed down by drag force, kind of like air resistance. But the blue areas? That represents the massive concentration of dark matter, mapped using gravitational lensing. Notice how the dark matter passed right through the collision totally unimpeded, moving way ahead of the hot gas? As this quote from NASA's Chandra X-ray Observatory points out, this separation is an absolute defining moment in astrophysics. If alternative theories of gravity were actually correct, the gravitational pull would be centered exactly where the mass of the hot pink gas is. But it's not. Instead, the gravity is centered on the blue areas, completely separate from the normal matter. Guys, it is direct, undeniable visual proof that dark matter is a distinct physical substance. It's not just a math error.
Section 4. The Particle Zoo Suspects.
All right, with dark matter proven to exist on a massive macro scale, the investigation makes a massive pivot. We have to transition from the telescope to the microscope to hunt down the actual microscopic quantum culprit. Welcome to the Particle Zoo. Let's lay out our lineup of top suspects. For a while, scientists thought maybe it was machos, massive compact halo objects, like rogue black holes or really faint stars. However, extensive gravitational lensing surveys have essentially ruled them out. There just simply aren't enough of them out there. So that leaves us searching for a brand new kind of subatomic particle, shifting the spotlight to cold dark matter candidates like WIMPs and axions.
For decades, the historic favorite has been WIMPs, weakly interacting massive particles. They neatly fit into a lot of extensions of the standard model of physics. However, highly sensitive underground detectors have consistently turned up completely empty-handed. Because of this, a rising star is taking over the spotlight, the axion. Axions are incredibly light particles that have a huge theoretical advantage because they also happen to solve a completely separate mystery in quantum mechanics known as the strong CP problem. They basically act as a mathematical missing link in physics.
But honestly, the theoretical particle zoo is vast, and astrophysicists clearly have a sense of humor with their naming conventions. I mean, we have WISPs, or weakly interacting slim particles. We even have PIMPs, which interact only at the immense Planck scale. Now, you might be wondering about standard neutrinos, which we absolutely know exist. Unfortunately, standard neutrinos are considered hot, dark matter. They're just too light, and they zip around way too fast to form that dense cosmic scaffolding we looked at earlier. For the universe to work the way it does, we absolutely need a cold, sluggish, dark matter candidate.
Section 5. The future of the hunt. So the suspect is at large, and the theoretical list is long. How are modern astrophysicists actively working to close this case today? Well, it requires a two-pronged attack from both ends of the universe's extreme scales. On the macro hunt, we have incredible new tools like the European Space Agency's Euclid Space Telescope. Euclid is currently out there on a mission to map the large-scale structure of the dark universe across space and time. By observing billions of galaxies out to 10 billion light-years and covering over a third of the entire sky, Euclid is going to test how dark matter has clumped together over cosmic history with unprecedented precision.
Down on the micro level, the hunt is equally cutting edge. Because we don't know exactly what dark matter is made of, the potential mass and signal frequencies of these particles cover an unbelievably broad range. To try and catch them, scientists at institutions like Fermilab are deploying new electronically tunable quantum detectors. These devices are meticulously designed to capture incredibly faint, weak signals that might just be produced by a dark matter particle briefly interacting with our normal world.
So the crucial point to take away from all this is that it's a continuous, actively evolving investigation. We started in step 1 by observing massive cosmic anomalies, like impossibly fast galaxies. Then in step 2, we actually confirmed the distinct physical existence of this mass using the absolute smoking gun of the bullet cluster. And now, in step 3, we are deeply embedded in a high-stakes quantum hunt through a wild zoo of exotic particle suspects.
And that brings us to the ultimate question. With massive new space telescopes charting the macro web and ultra-sensitive quantum detectors listening closely in the microdark, will we finally catch the universe's greatest ghost in our lifetime? Or does the cosmos have entirely new, unimaginable secrets left to reveal about the very fabric of reality? Keep looking up, keep asking questions, and thank you so much for joining me on this explainer.